Okay, 11.8. How do I use the margin of error to construct a confidence interval? So go ahead, copy that down, pause it if you need to. All right, so first you need to understand before you can do margin of error what a confidence interval is. So take a second to read through this page, pause the video, and then you'll have an idea what's going on and we'll go over it. All right, so in this example we have a pollster, right, taking a report, 50% of voters choose a Democratic candidate with a margin of error of 5%. All right, what's going on here is that we have a confidence interval that's given, and they just didn't write it out completely. So we have 50% of voters are going to choose a Democratic candidate, but we don't know if it's exactly 50% because they took a poll, which means we need to figure out what the lowest bound, what the highest bound could possibly be from our confidence interval. So since it says that whole plus or minus 5, it actually means it could be 5% above 50 or 5% below 50. So it could actually be anywhere from 45 to 55% of people somewhere in there, and that's our confidence interval, that are actually going to vote for the Democratic candidate. The reason we have this is simply sampling error. All right, when you take a sample of people in the classroom, someone else takes a sample of people in a different classroom, or you're taking different samples with different people, you're going to get slightly different answers. On the whole, they should be pretty close to being the same, but there'll be slight variations from one sample to the next. So that's why we give a confidence interval. All right, the margin of error, right, is the other part of it. That's the easier part, actually. The margin of error is simply found by taking two standard deviations, and it's the part that you add or subtract. So you notice over here I wrote 2 standard deviations. All right, that won't be hard to do. Trust me on that. 2 times a number is very, very basic. But the margin of error for this problem was 5%. So it wasn't hard to go 5 plus 50 and 50 minus the 5 to end up with our 45 and our 55%. So the margin of error is simply just that number that you add and subtract. So it must have been 2.5 was the standard deviation. 2 times 2.5 would come up with the 5. We would add it and subtract it, and that's it. And that's for proportions. All right. For means, it's constructed using the same, pretty much the same procedure. We're always going to be given the mean. All right. We're typically going to use 95%, which should be awesome and nice for us because 95% typically means 2 standard deviations. We talk about that previous class with the normal model. 95% is within 2 standard deviations of the mean. So here we see an example where they give us a 95% confidence interval, but we're using a mean instead of a proportion, whereas this question was percentages. This is an average from 72 up to 107. That U is actually pronounced mu. Okay, fancy word. You really don't need to know much more about it than that, but that's that. All right, so what are we saying when we have a 95% confidence interval? And this is one of those tough things for people to understand, and this is the background that throws people off a little bit. The actual math of it is a joke. You're going to do the mean plus or minus 2 standard deviations. So it will not be hard to take a number like 50 and then add and subtract 5. That will not be the hard part. The hard part is actually understanding what's going on. So let me try and give you a little background there. When we have a 95% confidence interval, okay, what we're saying is if repeated samples were taken, all right, and we computed 95% confidence interval for each sample, 95% of the intervals that we would create would contain the true mean, the true average. The same is true for this problem up here. If we did, this is a 90% confidence interval, but same idea. So 90% of the confidence intervals we would create when we sample the Democratic voters, right, or voters, I'm sorry, in general, 90% of the confidence intervals would contain the true proportion of people that plan to vote for the Democratic candidate. That's kind of what's going on. So again, it's a little bit of the background. The math of it is pretty easy. It's from here to here. Do a number, add and subtract, 2 times the standard deviation. There's not much to it. So let's go on to some questions, and you can see that it is fairly straightforward. So, beginning of the school year. Okay, school district implements a new physical fitness program. A student project involves monitoring how long it takes 11th graders to run a mile. The following data were taken mid-year. So what is the estimate of the population mean time it currently takes 11th graders to run a mile based on the following data, minutes, from a random sample of 10 students? So you're just going to go to your calculator, you're going to type it in, add them all up, divide by 10, and you end up with x bar is 7.9. So because we don't have a lot of data, all right, they create a simulation. okay, based on their results from the random sample. The following graph displays the results of 50 random samples, each with a sample of size 10. So, if you take a look at this curve, it's not perfect, but with simulation and with actual data, we rarely ever have a normal model. But can you kind of see how this is kind of working and looking a little bit like a normal curve? That's what you want to notice. So, in pretty much every single one of these questions, you're going to see something that looks somewhat normal, not perfect, but close enough that we can say that it is approximately normal. So, we can take and answer questions based off of it if it looks approximately normally distributed, which all of them will. So, we're going to be using the normal model over and over and over again. Now, I do believe you have an error on your paper. You need to change this number right here to say 8.1. Yours says 8.2, and I actually changed that when I changed the question. All right, so Jessica, an aspiring statistics student, wants to know if the new physical fitness program is worth all the extra work. She doesn't believe the new program is any better than last year's program, which had an average time, an average mean time of 8.1 minutes. Assume the set of data is approximately normal, and the students want to be 95% confident in their results. So we're assuming that it's approximately normal. That's a key word there. So now we can use the normal curve. And they want to be 95% confident. That's extremely important because we know that to be 95% confident, we need to fall within 2 standard deviations of the mean. Well, it just so happens, coincidentally, right, that when you take a look at it, the mean of means and the standard deviation of them worked out to be right on our paper. That will always happen. We will be given a simulation that looks approximately normal, or that they say will be approximately normal. They'll give us a mean, they'll give us a standard deviation, and we're going to figure out what would be within 95%. So to do that, we know that 95% is within 2 standard deviations of the mean. So it's going to be our sum number, that mean of 7.89 up here, plus or minus 2 standard deviations. Well, here's the standard deviation. So 2 times 0.186. So 7.89 plus or minus 0.36 will give us our range of values. Now, that margin of error is how much you're adding or subtracting to the middle number, the mean. So the margin of error for this problem is right here. This is our margin of error. So 7.89 plus 0.36 and 7.89 minus 0.36 will give us the value of our highest and lowest possibilities. So we say from 7.53 to 8.25. Now, just like with domain and with range, we can write this as an interval. So we're saying from 7.53 all the way up to 8.25 is our 95% confidence interval. And it says, the next question, or the part of the question that we care about, does last year's mean fall within the margin of error? Well, the margin of error says to take 0.36 and add it and subtract it to 7.89. It gives us this range of values. And so yes, from 7.53 to 8.25, last year's mean, which was 8.1, falls within the margin of error. So the answer is yes. 8.1 is in or within the margin of error. So yes, 8.1 is within the margin of error. When it says justify, you just need to show your work, which we have right here. So now we answer the question where we're using statistics. Is Jessica correct in her assumption, or does she need to eat some humble pie? Is she wrong? Okay, explain how the simulation supports your decision. So what we know is that the mean that we got from our sample was 7.89. And we want to know, is 8.1 a value that is really far from it, or is it a value that would occur due to random variations? So when we take a look at this simulation here, here is the 7.89 that we had. Okay, and we want to know, is 8.1 so far away that we can say it's really rare, or is it within the bounds that would occur due to random variations? It's very easy to tell what's within the bounds that occur due to random variations because you have a confidence interval, and your confidence interval tells you what are likely values to occur. So we have the 7.89 right here, right, plus or minus our 0.36. This gives us the bounds that would occur due to random variations. So when you take a sample and someone else takes a sample and someone else takes a sample and you sample different people, or in this case different averages, right, and get different averages from that sample, you're not going to have the exact same sample average. So we're going to end up with a variation of numbers. And this interval that we have here represents all the potential numbers that we could get. So from there, we have to then say, okay, is 8.1 inside this interval? And the answer is, yeah, it is. So 8.1 is inside the bounds that would occur due to just random variability or random sampling and coming up with a different answer. So we can say, yes, 8.1 falls within the sample. Therefore, Jessica is correct, and it is the same time. So our answer is Jessica is correct. And you know what? I'm going to pause it and write it, and then I'll let you guys copy it. So we're going to say Jessica is correct, since 8.1 is within our 95% confidence interval. I'm sorry, this is giving me a hard time. So what are we really saying when it's inside the 95% confidence interval? Let's go back to the problem just so we can make sure we understand it. So we did our sample. We wanted to see what would we get when we sampled those 10 people. And we found our sample to be at 7.9. So what does that mean? Well, it means the average was 7.9. But is everybody's average going to be 7.9? Of course not. Not everyone's average will be exactly 7.9. It's going to vary a little bit. And how much can it vary? Well, to find out how much it can vary, we create the 95% confidence interval. And we're always going to create 95% confidence interval, so you don't need to worry about any other. So we create our interval, and we say from 7.53 up to 8.25, somewhere in here. So anywhere in that region, we can now say, hey, it's the same as 7.9 because it could have varied. Remember we said at the beginning that we didn't know exactly what. We got 7.9, but everybody else might have gotten something a little different. So anywhere from here to here, anywhere in here, we can say it's essentially the same. It hasn't changed. Because of random variability, we could have got a sample that was as high as up here or as low as the 7.5. So since Jessica doesn't believe the new program is any better, right, she can say, yeah, it's not. All right, anywhere in here would still be the same. The new program is in fact no better because anywhere from here to here is the same as the 7.9, or could have been the same. Now, what happens if, right? What happens if that number wasn't 8.1 and it was 8.4? Well, if it's 8.4, okay, the old program is 8.4. What are we going to say? Well, if the old program is 8.4 minutes, not 8.1, and our interval is saying that it has to be, our new program at least, has to be between 7.53 and 8.25, we can conclude that the new program is worse and that the old program was better. Or we could have the other option happen is that it's down here, right? The old program was at like 7.2. Here's the old program, which now means the new program is clearly 100% above, right? All the values that we could potentially have, or 95%, I guess. But it's above. Our 95% confidence interval is above what the value is. If it's 7.2, we can say that the new program is better. But anywhere in here, we have to say it's the same, which means Jessica, of course, is correct. So this is where it's the same. This is where the
Up here again, this is where the old program would be better if it was 8.4, the old program. And again down here, this is where the old program would be worse and the new program would be better because the new program is clearly higher.
So take a second, read through this question, and then we'll show you how quick a question can actually go. It doesn't have to take as long as the last one. All right, so we have a hot dog company considering a new manufacturing technique for their low sodium hot dogs. The company will only switch if the average sodium is less than 350. All right, the following graph displays the results from 100 samples, 100 random samples, each with the sample size 10, based on the requirements that the average sodium level is 350. So here we have our mean of means and our standard deviation. Okay, so we have a nice normal looking curve. They're probably going to say it's approximately normal, and if they don't, well, the curve looks it, so we're good to go. So part A. So the mean sodium content is 363 is from the sample. Assume that it is approximately normal, and we want to be 95% confident. There's your plus or minus 2 standard deviations. Does the sample mean obtained fall within the margin of error developed? So we have to figure out our confidence interval, which is the mean plus or minus 2 standard deviations. So we have the mean up above at 349.68, and we're going to get going with that. So I'm going to pause it. So we have the mean, which is the 348. You see right above. Whoops, that was interesting. So the 348 that we have right up here is the mean. We put that first, plus or minus our 2 standard deviations, which they gave us right there. So we have 349.68 plus or minus 2 times the 5.66 is 11.32. And when you type in your calculator, that's what you get. You don't need to actually do that. You can just take my word for it. So we have a range of values from 338.36 up to 361. So is 363, does it fall within? Okay. Does the sample mean of 363 fall within the margin of error? Well, here we have it, and the answer is no. 363 is not within, so we can just say no. Oops, gotta get my pen. So no, it's not within the margin of error. Sorry, I apologize. The with, that's my abbreviation for with, W/. So on to the next part. Should the company continue with the new manufacturing technique? Meaning, is it going to be good enough? Well, our sample from the new manufacturing technique was 363, which is above the bounds that would occur, right? So 350 is the goal, right? If it is at 350, we're okay. So if 350 were correct, we would have a range of values from 338 up to 361. And any number that's in between there, I would say, hey, that could have been 350. Those are the bounds that would occur due to random variability. But my 363 that we got, that is above the bounds that would occur due to random variability, meaning it is more than likely higher than 350. So our answer to the company's question, should they continue with this new manufacturing technique, is no. It does not work. So let's get that written down. Pause the video here, and I'm going to write it down for you. All right, so there it is. The answer is no, since 363 is above our 95% confidence interval. And again, that confidence interval was from, there we go, 338 to 361. It is therefore above the bounds that would occur due to random variability. So here are the bounds that occur due to random variability. 363 is the number that we got. It is clearly above that. So our answer is no. We don't want to continue with the new manufacturing technique. If, however, though, it was like, let's say, 351 or 339, we could say, yeah, that's inside the bounds that would occur. If the true value really is 350, then anywhere from here to here is a number that you are likely to get. But again, it wasn't, so we can't say that it is. So we have to say no.
So we're going to say no, since 363 is above our 95% confidence interval. So again, our interval went from 338, we're just going to mark it over here, 338, come on, start working, 338, well that's not quite where it is, but you get the idea, up to 361. Okay, so anywhere in there is a value for what it could have been. Now, what are we talking about, in which direction? So you need to understand what the interval represented. So the interval was based off of the sodium level being 350. So if the sodium level truly is somewhere around 350, or 349.68, it could range as high as 361 or as low as 338. So anywhere between 338 and 361, we could totally be saying, yep, it's potentially 350. It's the same, okay? Any value that we got. But when they go and they get a value that's at 363, which is clearly above, 363 is clearly above, we have to say no, since 363 is above our interval, okay? Because they wanted it to be at 350. The average sodium level had to be at 350. So this is where it would be the same, okay? We could say it's the same, and we would say, yes, we're good to go. Even down here, we could say, yeah. If they got a value of 336 or 332, we would be okay with that because it's below that 350, right? So their 350 or less is what they're really looking for. They want to have low sodium hot dogs. So if they had below and they were over here, it'd still be okay to have. But since we're up here, right, this is where we have to say no, okay? Anywhere in here, we could say yes, it's still the same, or yes, it's actually better than what they wanted. And again, I'm sorry if I didn't mention it, I abbreviated confidence interval with CI, and you can get away with doing that, and you will be A-OK. Let's move on to the next one.
Take a second, read through the question. There's quite a bit to it. And then I'll go over it. I'm going to pause it, and so should you. So here's what's going on. So we have the Consumer Product Safety Commission, that's a mouthful to say, claimed that 90% of all homes have at least one detector. But this local city, they think that they've been doing a great campaign that's increased, or hoping that's increased their local level above the 90% rate. A building inspector, he goes to 400 randomly selected homes and finds 376 with smoke detectors. Okay, so they devised a simulation that we see down here of sample size 400, simulated 100 times, based on the requirement that 90% of the homes had one detector. So what they're saying is, if this value of 90% is in fact true, what would we expect to see when we did a sample? Because obviously, if you go into 100 homes, you're not going to see 90% have exactly every single time, 90 out of 100 homes. Sometimes it'll be 91, sometimes it'll be 92, sometimes it'll be 88 or 89, and you need to figure out what is a reasonable expectation. What could it fall within? So what are the bounds? Well, we already know that. We know how to do that. So the idea is we're going to do a 95% confidence interval for a sample mean of 0.9 with a standard deviation of 0.01. So here is our simulation. These are the results of the simulation, and they want us to figure out when we do our our 95% confidence interval, does the sample of 376 out of 400 fall within the margin of error? So I'm going to have to write really small here. Give me a second. So we're going to do our same thing, the mean, which is 0.9, plus or minus 2 standard deviations, and I believe the standard deviation is 0.01. Hopefully it is, because I can't see it. So 0.09 plus or minus 0.02, which gives us from 0.88 or 88% up to 92%. Okay, so from 88 up to 92. So again, if we were going into homes and we were, sampling 100 homes, we would expect to see, if the true rate of smoke detectors in the house is 90%, we would expect to see anything from 88 all the way up to 92, and that's what we would expect to see in a house. Anything that's less than that, we would have to say, hey, wait a minute, it looks like your numbers have gone down. Anything higher than 92%, and then we can say to them, it looks like your numbers are actually higher. So the question is saying, does the sample proportion of 376 out of 400 fall within the simulation, right, the margin of error of the simulation? So we have to figure that out. So our p hat, which is our sample proportion, we'll be talking more about that next class, but just for now you can trust me on that. P hat is what we use for our sample proportion, is going to equal 0.94. So now the question is 0.94 in the interval? Well, the obvious answer there is no, it's not. 0.94 is way over here. Come on. And our interval only goes from 0.88 up to 0.92. Okay? So that's where our interval is, and 0.94 is way above. So no, 0.94 is not within the margin of error. So the city decides that they can claim they have a higher rate of smoke detectors than the national rate. Describe how the simulation used to support this data. Well, where is 0.94? 0.94 is very, very clearly way above. All right, these are the answers from here to here, 0.88 all the way to 0.92 that you would expect to see if the true rate, right, in that town was 90%, which is what they say the national average was. So for it to be way above, the only thing that we can say is, well, this would not be likely to occur. This is a very rare number because it's outside of the 2 standard deviations. It's not likely to occur due to random variability. So yeah, they can claim it. I'm going to pause it, write that out, and then read it through for you.
So since the 0.94 or the 376 over 400, whichever one you want to use, is above our 95% confidence interval. Okay. And that's the reason why the city can describe or decide that they can claim that they have a higher rate. So what are the other possibilities? Well, let's take a look at it. So up here, the city can say anywhere over here they are higher, they're doing really good. Anywhere in here, the city has to say that they're the same. Okay? They are the same, they are no different. Any one of these numbers is just as likely to occur, it'd still be 90%. So if they had 89, somewhere in here, okay, 0.89, 0.889 or whatever the case that may be, they're going to have to say, nope, it's still pretty consistent. But the scary part is, if they're over here. So what if they were over here, what would we say? Well, we would have to say that it is lower, right, than the national average, and that wouldn't be good. Okay, so any place below 0.88, all right, we are lower, and they're worse than average. Don't forget to write the summary, the important concepts, ideas. Thank you.